Welcome back to the series on statistics. In this video I'm going to be deriving the moment generating functions for several of our familiar distributions. I'm going to start with binomial distributions, general form, and then I'm going to move towards the continuous uniform distribution and the normal distributions. So without further ado, let's get started. Alright, so let's get started here with the binomial distribution. We're told to let B be a binomially distributed random variable with n trials and a probability of success, so to speak, of P. We're asked to find the moment generating function of B. Okay, so we know from our definition of the moment generating function that this is just going to be equal to the expected value of e to the s, and then we need to institute some dummy variable here. I'm just going to use the letter b because it corresponds with our random variable as we denoted it. But you don't have to use b, you could use whatever you want. The important thing is that according to the law of the unconscious statistician, the expected value of some function here with that dummy variable is just going to be equal to, you would sum across all possible outcomes of the random variable, that function evaluated at that random variable, and then you want to multiply by the probability mass function in this case because we're dealing with the discrete distribution evaluated at that same variable. And so essentially, if this was, the expected value of x, so to speak, we'd be dealing with the mean, but we would just be taking the sum of x times the probability mass function across all possible trials. We're going to do the exact same thing here, but we're just going to do it with our function. And that comes from the law of the unconscious statistician. One important caveat is that the variable in the function that we're dealing with, so in this case it's b, that needs to correspond with the variable in the probability mass function. And so you would think we would be integrating with respect to this variable, so we're going to do essentially the exact same thing here. We're going to sum across all possible values, but our index is going to correspond to that variable. And so we're going to sum over all the possible outcomes here. And then we should recall from our video of the binomial distribution, or if we've taken a statistics class, that the probability mass function for a binomial distribution is going to be the number of trials, choose the particular outcome. So here we're indexing from b is 0 to all the way up to n possible successes. And then we're going to do the probability of success to the power of b times 1 minus probability of success. This is giving us a, so to speak, probability of failure to the power of n minus b. And so this right here, this is just the probability mass function for the binomial distribution. And so now we have our moment generating function. This is it. This is correct. This is the answer. But we obviously want to reduce this into a form that's more easy to work with. And so I am immediately noticing that this e to the sb and this p to the b, we could sort of squeeze these things together, and we can get that this is equal to the sum from b is equal to 0 all the way up to n of n choose b times e to the s multiplied by p to the power of b times 1 minus p to the power of n minus b. And you might be wondering, why is this a preferable format to what we have up here? This is about as complicated as the first. But the reason is, if we recall, our binomial theorem, this tells us if we have two variables to the power of something, this is just going to be the sum from, let's say, I is equal to 0 to n of n choose I, of x to the power of I, y to the n minus I. This is our binomial theorem. Should be familiar with this. But if we're not, I encourage you to plug in a couple values here and test this out for yourself. You see that it works. This is exactly the format that we have here. So this is just n choose b. The only thing that's changed here is the index and the variables. They're just expressions at this point. But what this allows us to do is that we could convert it into this format, which is a lot easier to work with. And so here, this would be our x, and this would be our y. And so we could say that this is just equal to e to the s p plus 1 minus p, all of that to the power of n. And we could reduce this just a little bit further just by manipulating this. This would be p times e to the s minus 1 plus 1 to the power of n. And this would then be our moment generating function for the binomial distribution. And if we wanted to check our answer here, we could just check that if we took the first derivative here and evaluated it at s equals 0, we should get the mean of a binomial distribution. So if we did that, we would get, let's see, this would be the chain rule, so this would just be n times this whole entire expression here It's 1 to the power of n minus 1. And then we would need to multiply by the derivative of the inside with respect to the variable s. And so that would just be, we'd multiply by p to the es. And that would be the first derivative, but remember we need to evaluate where s is equal to 0. And when s is equal to 0, this is going to go to 1, so we'd have 1 minus 1, so it's going to be 0, and that will cancel with the p, and then we just have 1 to the power of n minus 1, 1 to the power of anything is just itself, it's just 1, and so we get n here, and then here we get e to the 0 is equal to 1, and so this is just going to be np, and that is the mean of a binomial distribution. So at least it appears ostensibly that we have the correct answer here. I wanted to use this as an example because, finding the expected value of this function is exactly the same for discrete distributions as it is for continuous distributions. It's just that the format is a little bit different. Instead of integrating, we could just take the sum across all the possible outcomes. We don't have to integrate because we're not dealing with infinitely many infinitesimal possibilities. We're dealing with discrete cases. And so this is an example of finding the moment generating function for a discrete probability distribution. Now let's move forward towards our first continuous distribution that we heard of, the uniform distribution. And so we're told to let y be a uniformly distributed random variable in the interval from a to b, and we're asked to find the moment generating function of y. And so we know from our formula that the moment generating function for a random variable or a probability distribution is just the expected value of e to the s and then some dummy variable here that we're going to be integrating with. I'll use y since it corresponds to the letter of the random variable. And so if we wanted to actually carry out this operation, we would have to integrate over all the values in the support. So this is going to be a uniform distribution on the interval from a to b. So we'll be integrating from a to b. And then we need to substitute in our function here according to the law of the unconscious statistician, and then we're multiplying by the probability density function in this case. This is a continuous distribution, and the probability density function for a uniform distribution on an interval from a to b is just going to be a constant. It'll be 1 over the length of the interval. And we're integrating here with respect to y. And so this is going to give us our moment generating function. Let's actually carry out this operation here. And really, this is actually very simple. This is just a constant, so we can just pull it out of the interval. And then this just becomes the integral from a to b of e to the sy with respect to y. And this is actually very easy to evaluate. Of course, if you took the derivative here, you would have to pull out this s according to the chain rule. And so the antiderivative would just be 1 over s times e to the sy. And so this is just going to be 1 over b minus a times 1 over s e to the sy evaluated at y is equal to a, y is equal to b. And so what is this going to give us? So this will give us 1 over b minus a, and then this 1 over s is going to be there for both of these variables. So I'll just pull it into this constant multiple out front. So it'll be 1 over s times b minus a, and then we'd have e to the sb minus e to the sa. And so this is going to be multiplied by e to the sb minus e to the sa. Okay. So we get a final answer of, let's see, we'll just turn this into a fraction. We get e to the sb minus e to the sa, all of this over s times b minus a. And that's going to be our moment generating function for a uniform distribution. Now I'm going to come back to this moment generating function at the end of the video. This is a very simple integral, so I'm sure you will not expect that there were any mistakes here that were made. But if you try to actually evaluate this, like if you try to take the first derivative and evaluate it as equals 0, or the second, or the third, you'll find, first of all, that the complexity is annoying, to say the least. And second of all, it appears to be undefined. Like when we have a 1 over s here, so when we're differentiating with respect to s, you can imagine that there's going to be a natural logarithm that will show up there. And if you take the natural log, evaluate it at 0, because we would be evaluating the derivative at s equals 0, that's a error. Like you're not going to get an answer that you can't have the natural log of 0. And so this is somewhat interesting. This is the correct moment generating function, but it's not very easy to find the moments from this moment generating function. So I'll return to this at the end of the video if you're curious at all about how to actually do that and why these errors are actually showing up. But for now, I should move forward because I want to kind of contain that at the end of the video just for those who are interested. All right, so now let's move on to our favorite distribution, the normal distribution. We're told to let x be a normally distributed random variable with a mean of mu and a variance of sigma squared. And we're told to find the moment generating function of x. Before we actually do that, I'm going to find the moment generating function for a standard normal distribution because it's a lot easier to find that and then move forward based off of that information. And you'll see more about why that makes sense as we actually work through the steps. But essentially, we're just going to let z be a normally distributed random variable with a mean of mu and a variance of 1. And we're going to find the moment generating function for z first. And so by the definition of the moment generating function, this is just going to be equal to, let's see, this is the expected value of e to the s. I'll use z in this case, just to keep it distinct from our x variable that we're actually trying to solve for. And so just in keeping with the definition of expected value, this is according to the law of the unconscious statistician, this is just e to the sz multiplied by the probability density function for the standard normal distribution here, which is the 1 over the square root of 2 pi, e to the negative 1/2, and then we'd have z squared here, and we would be integrating with respect to z. And so if we actually want to solve this integral, we could squeeze these two e's together. We could pull this constant out, and so we'd have 1 over the square root of 2 pi, and then we'd integrate from negative infinity to infinity, and then here we could pull these together, and so we would have e to the negative 1/2 z squared plus sz dz. Now the easiest way to actually solve this integral is to complete the square up here in the exponent. This is the traditional way that this is done. And so that's not very hard. We'll just do 1 over the square root of 2 pi. This constant will stay the same. Then we're integrating across all the values in the support. And then we have to pull out this factor of a 1/2. And so this would be e to the 1/2. I mean, I suppose we don't have to do this, but it does make it easier. Z squared and then minus 2sz. And then we can immediately recognize if we want this to be a perfect square polynomial, we would just need to add the constant of s squared here. But then we need to realize that we're adding a constant of s squared multiplied by negative 1/2. And so if we want this to be the same, we need to add s squared over 2 here. And then this will cancel with this, and this is exactly the same as this expression here. So this is the same. But then what we can do is, since we're integrating with respect to z and not s, we could separate the variables here. And so we could do, this is e to this power times e to this power, and then we could pull that constant out. That e to this power is just going to be some constant because we're integrating with respect to z. We could just pull it out of the integral. And so this is going to be e to the s squared over 2. And then I'm actually going to pop this constant back inside the integral. I shouldn't have pulled it out, but it's just intuition. Every time I see a constant, I want to pull it out of the integral. And the reason I'm going to pop this back in, you will see in a second, is that this is going to become e to the 1/2, and then this is just z minus s squared. And so this is z minus s squared with respect to z. And now we can solve this very quickly by just using u substitution. If we say that u is equal to z minus s, then du, which is going to be dz. And so we can just sub this in directly. And I'm sure you'll agree, if you look at the bounds of the integral, we have the limit as z goes to infinity of this u is just going to go to infinity as well, and the same is true for negative infinity. So these bounds aren't going to change. And so we're going to have e to the s squared over 2 times the integral from negative infinity to infinity of 1 over the square root of 2 pi times e to the negative 1/2 u squared du. And what is this? This is just the standard normal distribution, the probability density function for the standard normal distribution. And if we integrate across all possible values under the probability density function, what is that going to give us? It's just going to give us a value of 1. And so I guess I should notate that. It's just be 1. We're integrating across all values in the support across the PDF. Or I guess I'm using the variable u here. And so this has to be equal to 1 by definition of the probability density function, and so we're done. We found the moment generating function for the standard normal distribution. I'm going to write it this way because I think it looks better. And so this is our moment generating function for a standard normal distribution. And so I'm going to box this just because this might be useful at times. You might want to know the moment generating function of the standard normal distribution, but what will be more useful is the moment generating function for the general normal distribution. And the way we're going to get to that from this is we're going to recognize that if there's a fact that we have already established, which is that if you take a randomly distributed or a normally distributed random variable with a mean of mu and a standard deviation of sigma, if you sort of calculate a z-score, so you take the difference from the mean and you divide by the standard deviation, this z-score is going to be normally distributed, and so this is going to be equal to our standard normal distribution. But we can sort of rearrange this fact to tell us that our general normal distribution is going to be equal to sigma times our standard normal distribution plus a mean of mu. And we could use this fact to find the moment generating function for our general normal distribution. And so how would we do that? We know that we can sort of take this up here, and we know that the moment generating function of our random variable here, this is just going to be the expected value of, we do e to the s, it's a dummy variable there. But we know that if we were sort of to plug this expression in here for x, we'd say that this is equal to the expected value of e to the s times, then we'd have sigma z plus mu. And we can sort of distribute out that s here, and so we get that this is equal to the expected value of e to the s sigma z plus s mu. And now here, if we were to carry this out, we're integrating with respect to z, right? This function multiplied by the probability density function of z. That's what we would be doing. And so if we were to rearrange this as the product of two exponentials, we would have e to the s sigma z plus times e to the s mu. This portion of it would just become a constant, right? Because we would be integrating with respect to z, not with respect to s. And so I'm sure you would agree that this would become e to the s mu multiplied by the expected value of e to the s sigma z. And now the big shortcut that we have to carry out here is that we don't actually have to integrate at all, because if we just realize that this expected value of e to the s sigma z, if we were to take the moment generating function of z, evaluated at, let's see, s sigma, what would that give us? This would give us the expected value of e to the s sigma z, according to that normal distribution, or that standard normal distribution. And that's exactly what we have here. So this is just the moment generating function for our standard normal distribution evaluated at s sigma. That's what this is going to reduce to. And so we could just plug in s sigma into our moment generating function that we have for the standard normal distribution, and we get that our answer here is going to be e to the s times our mu multiplied by e to the, and then we just plug in s sigma here, and so we get 1/2 s sigma squared. And so this is our moment generating function, but we can rearrange this just a little bit, and we'll get that our moment generating function for a general normal distribution is just going to be equal to e to the 1/2 s sigma squared plus s times our mean. And so this is our answer here. This is the moment generating function for a general normal distribution. All right, so I promised I would come back to this at the end of the video. This is our moment generating function for a uniform distribution, a continuous uniform distribution. And I pointed out that some of you may have noticed already, but I pointed out earlier in the video that if you try to actually evaluate the moments from this distribution, you're just going to get errors. It won't be defined. And so we might be curious what's going on here. Technically, I lied. This is not the full moment generating function for this distribution. Technically, the full definition for the moment generating function of this distribution is going to be a piecewise function. And so this is going to be some piecewise function. That is the worst bracket I've ever seen. But if we evaluate this when, you would see if s is equal, or I guess I could just write the expression. You would have e to the sb minus e to the sa. divided by s times b minus a when s is not equal to 0, and it's just going to be equal to 1 when s is equal to 0. And so this is the actual, the full moment generating function, and it stems from the fact that the actual PDF for that distribution, the PDF for this distribution, is going to be equal to 1 over b minus a, 1 over b minus a, when x is on the interval, or when I guess in this case when s is on the interval from b to a, but it's going to be 0 otherwise. 0 otherwise. And so I'm not going to explain the connection between this and this, because the honest truth is I don't really understand it myself. I'm not really sure how to get these expected values from piecewise functions and find them. So I dealt with the sort of non-trivial case, which is this one right here. I mean, obviously, every derivative of 1 is going to be equal to 0. So I guess it kind of explains the moments from that part of the distribution. But what I do want to show is that you can get the moments from this moment generating function here. You can actually get them because the function is not defined at 0, but the limit as the function approaches 0 is defined. And from our video on moments, you might expect that that's actually more important than the function being defined at that point. Because what we are interested in is the rates of change, the first rate of change, and then the rate of change of the rate of change, and then proceeding in that manner all the way down. That's actually the information that is characterizing the distribution. And so if we want to actually find that, we have to use a couple different properties. The first one is if we have some series, I would say Sn, and this is given by 1 plus r squared plus r cubed plus ... and we do r to the, let's say, n minus 1 here. If we have this series, we can actually find a formula for this series that's going to be important in sort of unpacking this moment generating function, or I guess it's a step towards that. If we were to take r times this series, we'll just get r plus r squared plus ... and we get r to the n. And so if we were to take r times the series and subtract the original series, what are we going to get? Every term in here is going to cancel. And so we cancel everything, and we'd be left with r to the n plus 1. And we can sort of factor out the series itself here, and we'll get that our series here times r minus 1 is equal to r to the n plus 1. And so we could solve for our series here. This series is going to be r to the n plus 1 divided by r minus 1. Now, why is this fact useful? This fact is useful because if we let r equal x over y, for example, then what are we going to get over here? We'll have x over y to the power of n plus 1 divided by x over y minus 1. What is this going to be equal to? Well, here we'd get 1 plus x over y plus x over y squared plus x over y to the n minus 1. I promise you that this is going somewhere. And so now, if we want to, what we have to do here is we'd have to multiply by the denominator here. And so we get rid of that. And so we get x over y to the n plus 1. This is going to equal x over y minus 1 times this whole series here. I'm not going to rewrite all of this, but this is going to go in there. And now all I want to do here is I want to multiply both sides of this equation by y to the n. By y to the n. If I take this whole side here and I multiply by y to the n, what am I going to get? Here on this side, y to the n will cancel with the y to the n in the denominator here, and I'll be left with x to the n. And then here, what am I going to get? Actually, I realized I made a mistake here. When I subtracted this r s to the n, I subtracted the first series here, so this should be a minus 1. That's what this should be. It should be a minus 1. minus 1, minus 1, minus 1. And so this is going to be x to the n minus y to the n. And then what am I going to get on the right side here when I multiply by y to the n? Well, I can break this up since this is just a product in here, and I can multiply by y here, and I can multiply by y to the n minus 1 here. And obviously that's going to cause a much easier cancellation here, right? And so what would I get if I carried out this operation that way? If I multiply by y here, I would get x minus y. The y would cancel the denominator here. We get x minus y. And then here on the left, or on the right side here, what am I going to get? Well, I get y to the n minus 1. And then one of those would cancel, and I get plus x times y to the n minus 2. And then this is going to proceed. And then the very last term here, I'd have y to the n minus 1 minus times x to the n minus 1 divided by y to the n minus 1. And so that would cancel it. We just have plus x to the n minus 1. And so that would be when we would get there. And what does this allow us to do? This allows us to generalize the difference of squares formula. So you may have seen that x squared minus y squared. You've definitely probably seen this. This is just x plus y times x minus y. But we can actually get, we can always factor out sort of this x minus y here for all of these distributions. This is according to this formula. And so the way that this is the way that it's derived, but this is essentially, you can instantly sort of recognize the pattern here, but this tells us that x to the n minus y to the n is just going to be equal to x minus y times the sum here from I is equal to 0 to n minus 1. And so here, you could swap these variables. It doesn't matter because it's the same front to back. And so this is just going to be y to the power of, let's say, the way that I've written it here, this would be y to the power of n minus 1 minus I, and then multiplied by x to the power of I. And so this sort of generalizes this difference of two powers formula. And we're going to need to use this right here. And so I need to show where that came from. All right, so I moved that up here because if we want to calculate the moments from this moment generating function, we're actually going to convert this to a different format. We're going to have to use this fact in order to do that. And so the first thing that we're going to do is we're going to sort of unpack these exponentials by using the Taylor series, the Maclaurin series. I always forget which one. But this is just going to be 1 over s times b minus a multiplied by the infinite sum from I is equal to 0. And then here, the Maclaurin series for these exponentials, this is just going to be sb to the power of I minus sa to the power of I divided by, they will share a common factor of I factorial. And then here, just to rearrange this a little bit, I want to pull out this anything that has to do with the s term here. And so this is going to be 1 over s times b minus a. Once again, the infinite sum from I is equal to 0. And now we would have s to the power of I divided by I factorial times b to the I minus a to the I. And the reason that I want to do this is because this allows us to use this difference of powers here, this b to the I minus a to the I. I can use this formula for our difference of powers to pull out this factor of b minus a and cancel with this b minus a in the denominator here. And I can use this s to the power of I. I can cancel one of those s's with this s here. And so I could get rid of that that coefficient out front. And I could say that the moment generating function for our uniform distribution is going to be equal to the infinite sum from I is equal to 0 of s, and then this will become s to the I minus 1, s to the I minus 1 over I factorial. And then this b to the I minus a to the I, I'm going to pull out a factor of b minus a, and so this is also going to turn into a sum from k is equal to 0. I need to change the sum here. And then what is this going to go to? Here, when we have a difference of powers of x to the n, we pull out that factor, and then we index from I is equal to 0 to n minus 1. And so here, since we had a difference of powers of I, this is going to go up to I minus 1. And then we just have b to the power of I minus 1 minus k times a to the power of k. That's just according to this difference of powers formula that we derived earlier. And so this is an alternative way of expressing this formula. These two equations are exactly equal, which I think is just fascinating. This is why I love mathematics. You have this infinite sum that's sort of nested inside each term, and that infinite sum, there's another summation. If you were to carry out this operation, you would get this function up here. These two expressions are exactly equal. But the reason that I want this expression in this form is because it becomes a lot easier to take derivatives. And so what do I mean by that? We sort of touched on this in the last video on moment generating functions, but if you have some variable to some power, let's say the third power, if you take the third derivative of this, you're just going to get 3t squared, 6t, 6, and then any derivative after that is going to be equal to 0. And so if you have some expression to the nth power, and you take the nth derivative, you're going to get some constant, and everything past that is going to go to 0. But also everything before that is still going to have that variable present in the expression. And so if you were to take the nth derivative, evaluate it at where that variable is equal to 0, then every term before that will also go to 0. And so that allows us to sort of take this infinite sum, and if we're taking the nth derivative and evaluating where s is equal to 0, only one term in the sum is going to remain. So we can collapse this infinite sum into just one term, just by virtue of that fact. And so that's what we're going to do, because if you take the nth derivative of this expression here, evaluated where s is equal to 0, that's just going to give us the nth moment of our uniform distribution. And so if we were to actually carry that out, we would have the nth derivative here of our moment generating function with respect to s. We're taking the derivative with respect to s, evaluated at s is equal to 0. What is this going to be equal to? So here, this is the only part that we're dealing with that has an s, so this is really the only thing we need to worry about. The only term that's going to remain when we take the nth derivative is going to be s to the power of n. And so we want I minus 1 to equal n. When is that going to happen? That's going to happen when I is equal to n plus 1. Right? And so this is going to be the only term that remains, and when I is equal to n plus 1, we're going to have s to the power of n divided by n plus 1 factorial. And when we took the nth derivative here, the numerator is just going to go to 1, and then we have, we're going to pull out this n times n minus 1 times n minus 2, and essentially every term in this factorial is going to be canceled except for the first term, that n plus 1. And so the nth derivative of this is just going to be 1 over n plus 1. And that's the only term in this infinite sum that's going to remain when we take the nth derivative and evaluate it at s is equal to 0. So we're going to be left with just 1 over n plus 1. Actually, I'm going to leave that. We'll have 1 over n plus 1. And then I minus 1 here needs to be equal to n. And so this series here, the sum here, is just going to be indexed from k is equal to 0. And now we're only going up to n. And similarly, we could plug in here. So we go b to the n minus k times a to the k. And so this expression here is going to give us our moments. Our nth moment is going to be given by this formula here. And we can actually rewrite this a little bit more simply because this 1 over n plus 1 does not depend on the index of this summation. And so we're going to get that the nth moment of our uniform distribution will be given by the sum here, k is equal to 0 to n, of b to the n minus k, a to the k, over n plus 1. And so this is going to give us our moments of our uniform distribution. And let's just sort of test this out to see if this is even accurate. If we want the first moment of our distribution, that would tell us to go to index from k is equal to 0 to 1. The first term in our series would be b to the power of 1 minus 0 times a to the power of 0. So that's just going to be b. And then we'd be dividing by 2. And then the second term in our sum here is going to be b to the power of 1 minus 1, which is just 0, times a to the power of 1. And so this is going to be a divided by 2. And so we get b plus a divided by 2. And that is the mean of a uniform distribution. So this sum here is going to give us our nth moments of the distribution, and we could get to this from our moment generating function. It just took a lot of work, And you can imagine it's a lot easier to calculate these moments just by using the definition of the nth moment of a distribution, and just calculating them individually would take a lot less work than deriving this moment generating function and expanding all of these exponentials and then finding this formula that allows us to calculate these moments. So these moment generating functions are more useful for other applications. They're usually not primarily used to calculate moments, despite what their name suggests. They're usually used to characterize distributions. And so I hope this video was interesting. I hope that was informative. I know it got a little bit complicated at the end, but I hope that was at least cool that you could see that this could be unpacked and actually utilized when at first it appeared to be undefined completely. Yeah, in the next video, we're going to use these moment generating functions to show that the distribution of sampled means, the distribution of sampled means, as the sample size goes to infinity, as the sample size increases, if you take the limit, the moment generating function of that will equal the moment generating function for a normal distribution. And that's going to be the central limit theorem. We're going to try to prove that with these moment generating functions. The implications of that allow us to use the normal distribution to characterize probabilities whenever we have a sufficient sample size. And what a sufficient sample size is, we'll talk a bit more about in the next video. But that's the direction we're going. And then after that, we're going to actually show, finally, how to practically solve these normal distribution problems after we have an understanding of why they're even useful in the first place. And then once again, I sort of said this in the last 3 videos, but beyond that, we'll just talk about hypothesis testing and confidence intervals, and then that will conclude the Statistics 1 series. So thank you guys for watching. Hope you guys enjoyed. See you all in the next one.